I went to the EF event on cryptographic resilience.
Oh, okay.
There were some solid talks there.
Nice. All right. Yeah, I actually haven't been to one of these events, so I don't know what it's like. But that sounds like the EF events sounds like it would be really good. You want to share a particular talk topic you thought was especially good?
Well, I'm a little biased. My teammate gave a talk on fuzzing, but besides that, I like Dimitri's talk on hashes. Gave a pretty good history of them and just general overview of the state of hashing now and how people think about them and what can be done about potential attacks.
Nice. Okay. So it was all about snark friendly hashes and kind of their cryptanalysis and that was the whole focus.
Yeah, I think it also covered non-snark friendly hashes as well.
Oh, okay. Yeah, I mean the process of how NIST selected Ketchak for SHA-3, how people actually design and cryptanalyze these standard hashes is actually pretty mysterious to me too. I would be interested in learning more about that in addition to the snark friendly ones. Is there a one sentence summary of sort of the state of, I know there's been all these efforts with Poseidon 2 and others to sort of make them both fast without proving and fast for proving. Is there kind of a one sentence summary of what the state of affairs is now?
I don't know if I have a good summary of that. From my sense, it's just it's a lot of magic. It's a lot of we do a lot of crazy stuff in one section, and the rest is really light, and then that ends up being fast. And
Okay.
also, I guess in both native and circuit form.
Yeah. Interesting. Okay. So yeah, thanks for sharing. Actually, I'm really interested to hear that, and maybe I'll look to see if there's a recording of the talk or something. I have there are some updates coming out early next week, which I think will make sort of standard hashes, turn out to be much friendlier to snarks than people think of them today. Which might, I guess we'll see how people react, might change the situation a bit. But yeah, so I think last time, if I remember right, because it was 2 weeks ago, I think this session we covered bulletproofs. Correct me if I'm wrong. Also known as IPA. And I think this time we're going to begin the discussion of recursive snarks and snark composition. And I think so next week's an off week because of Thanksgiving, but we'll come back the following week. But because there's some new stuff coming out next week, some new work. It's mostly not my work, but it's work I think is impactful. It's related to hashing-based polynomial commitments. So bulletproofs is not hashing-based. It's based on elliptic curve groups and such. And I don't think in this pass through the book we've discussed hashing-based polynomial commitments in detail, although everything blends together in my head now, so maybe I'm wrong about that, but it's certainly been long enough we can discuss them again. So these are things like Fry, Laharo, and Breakdown. And so with this new work coming out, which is related to these hashing-based polynomial commitments, this is what I think we'll discuss after Thanksgiving. And then we'll come back to finish up recursive snarks, and in particular cover Nova. As today we're not gonna get all the way to Nova. So that's my plan content-wise. I guess that'll take us to getting the middle of December. And actually, after we discuss all of this, we're pretty much done. I think there's a couple of other topics we could cover, but they're sort of much less central than everything I just listed above. We could discuss like the Dory inner polynomial commitment scheme, which is I think very, very interesting and very beautiful ideas, but not super popular in practice, and it's pretty complicated. So and maybe some other stuff if I think about it a bit. So we could keep going beyond the middle of December, or we could sort of call it a wrap. I've noticed at least a couple people in the chat have said they're interested in sort of starting from scratch, which we could do in the new year. So anyway, that'll be a topic for discussion later, but at least wanted to cover the plan for today and the next couple weeks following that. So let me just pause here, see if anyone wants to ask any questions. All right, and so hopefully I'm right that we last discussed bulletproofs. So now let's talk about snark composition. So I like to introduce snark composition with the following motivation. So imagine we have like a snark with like a really fast prover, but the proofs are bigger than we would like. So somewhat large verification costs. Okay, and this is actually this new work I'm teasing coming out next week. This is exactly the situation in that work. So nice fast prover, but the verification costs, like the proof size and verifier time, are square root in the size of the statement being proven. So say like n is the size of the circuit the prover is claiming to know a satisfying assignment for. Right. So in terms of like concrete proof size, I don't know, maybe the square root n means something like about 1 megabyte size proofs. I don't know, something like that. When we'd really like our proofs to be at most, I don't know, say 200 kilobytes or something. Who knows? So we're not happy with the proof size. So then imagine that we have a second snark, which has a slower prover. So not, impossibly slow, but not as fast the prover as our first snark, but smaller proofs. Say we're satisfied with the proof size of the second snark. It's got 200 kilobytes rather than 1 megabyte size proofs. Okay, so the question of composition then is, can we sort of combine these two snarks in some way to get the best of both worlds? So the fast prover of the first snark, but the nice verification costs of the second snark. Okay, and at least in principle, the answer is yes. And you just do it directly through composition. Okay, so what that means is sort of the snark prover in its head. What it first does is use the first snark. Let me call this snark 1. So it generates a proof of its claim. It's claiming to know a satisfying circuit. Let's say C is the circuit. So the prover is claiming to know a W such that C of W equals 1. So it generates a proof of this claim that it knows this W using snark 1. Okay, but that proof is a little bit big. So let's call that proof pi. So it doesn't actually send that proof to the verifier. Okay, instead what it does is it uses snark 2 to prove that it knows pi. Okay. And let's call that proof pi prime. That's the proof it sends to the verifier to be verified. Okay. And so what's happening here is we're applying snark 2 not to the original circuit C, but to the circuit that implements the verifier of snark 1. Okay. So, the prover, had to, in order to get to generate pi prime, right? The prover first had to generate pi, because pi is the witness for the statement it applies snark 2 to. The statement it applies snark 2 to is, I know a proof pi that the snark1 verifier would accept. So the witness to that statement is pi. So the prover had to generate pi and then generate pi prime, the snark 2 proof. But the verifier is just a snark 2 verifier, and that snark 2 verifier is looking only at the statements. Right. I know a proof that the snark 1 verifier would have accepted. So that is snark composition. And let's just think about the cost real fast. So from the verifier's perspective, like the verifier is only exposed to a snark 2 proof. So the verifier costs all come from snark 2. Right. So like the proof size and how long it takes to check the proof, well, it's just a snark 2 proof. So that's great. And then as far as the prover costs go, like P applies, the snark 1 proving procedure to the original circuit C, and then to get the witness pi for the second statement that snark 2 gets applied to, and then applies the snark 2 prover to the circuit C prime, which implements the snark 1 verifier. And the point is, at least in principle, the snark 1 verifier runs in time sublinear in the size of C. So if C had size n, the snark 1 verifier has size root n, which means when you turn it into a circuit C prime, like C prime has size about root n. And concretely, it's gross, as we'll discuss, to take a snark verifier and turn it into a circuit. So there's some gross hidden constant or something, but basically C prime has size, like root n, is roughly, whereas SC has size n. Okay, so the point is that while like snark 2 prover is slow, that slow prover is only getting applied to a small circuit, applied to a circuit of size root n. And the point is that applying like a pretty slow prover to a small circuit should still be a low order cost relative to applying a fast prover to a big circuit. Okay, so the goal in recursion is sort of just to make the snark 1 verifier efficient enough that the recursive proving, so the applying snark 2 prover to the verifier of snark 1 is not a bottleneck. It's like a low order cost relative to just applying the original snark to the original circuit. And as long as that's the case, you get the fast prover of snark 1 and the fast verifier and small proofs of snark 2. Okay. Any questions about that? All right. So I want to discuss a few issues that come up with this. I think the first one is, I guess, like engineering, and concrete performance issues, particularly with making sure that the circuit C prime implementing the snark 1 verifier is concretely not too big. So this especially dealing with making sure C prime is not too big. And then I want to discuss like security, let's say security analysis of in snark composition. Okay, so let's start with the engineering issues. So the main thing that comes up when you actually try to implement snark composition or recursion is, in terms of making it all work out in practice, is the following. Snark verifiers do a lot of cryptography. And what cryptography they do depends entirely on the polynomial commitment scheme that snark 1 uses. And so it's either hashing, a lot of hashing, or it's a lot of elliptic curve group operations. Okay, that's typically the cryptography, that snarks use and that the verifier has to do. Okay, and generally speaking, like doing cryptography in a circuit um, is gross. So and this is we just had a conversation before everyone got here about snark friendly hashes, which there was a survey given at in Istanbul. If you want a snark to like force the prover to correctly evaluate a hash function many times, right? You have to actually implement the hash function like in constraints or like in a circuit. And the hash functions we use today, well, they were designed to be fast on like real computers, but not necessarily on these like idealized circuits involving addition and multiplication operations or whatever that the kinds of circuits that snarks tend to consume, for example. So there's been a lot of work trying to identify hash functions such that when you turn, you can efficiently implement a hash function in a circuit, and thereby make sure that you can take something like the Fry verifier, which does a lot of hashes, and implement that verifier as a circuit and have the circuit not be huge. So let me say work on snark friendly hashes. There's been a lot of this. Let me just briefly state the names of some of these works, just for context, as you go out into this space. So maybe okay, actually, the first snark-friendly hash, people I think have forgotten the first work that did it. Looked at something called iTie's hash function, based on lattices. I don't think people use this much today. I actually think this is underappreciated, and things like this will make a comeback. But what people, have focused on today, so there's Poseidon. Others you've probably encountered. Let's see, we got rescue hash, reinforced concrete. There's Poseidon 2, which I forget if that was sort of meant to avoid certain attacks or just to be faster hash function on the CPU. I forget what aspects of Poseidon people were trying to improve there. And there are a bunch more. So just giving you some names so you can look out for them. And my general view, which I know I'm not alone in, is that this is natural to pursue and understand, but I'm a little trepidatious that the security of these hash functions is not as well understood. They're new. They haven't been cryptanalyzed as much as thoroughly as something like a NIST standard. And my other view, which is more controversial, and which I'm going to try to push in next week, is that these snark friendly hashes have sort of been designed to be friendly to like the current generation of snarks. But just as my one of my goals with Jolt was to show that like general computer architectures that were not designed to be snark friendly, like the RISC-V instruction set, actually are as snark friendly as anything else. I think that, in fact, a bunch of hash functions that were not designed to be snark friendly are basically as snark friendly as anything else. So anyway, we'll see what happens with this hashing stuff. But yeah, just a huge amount of work, which to date has been really important in making sure that we can take these snark verifiers that do a lot of hashing and turn them into circuits that aren't too big, so then we can recursively prove knowledge of satisfying assignments to those circuits. Let's see. Yeah, okay. So then let's talk about elliptic curve group ops, which there's more to say about that. So yeah, snarks that involve elliptic curve group ops, anything that uses KZG commitments, that's the most important example. So this would be Growth 16, Marlin, Planck. These were all at least initially described using KZG commitments to keep the proof short. although you can swap in any other polynomial commitment scheme. Bulletproofs from last week is another example, but you have an issue there that I'll get to later. Don't let me forget to mention, let me just make a note. Remember to discuss bulletproofs, and recursion, and in particular Halo, which ultimately started a line of work leading to Nova, which again we'll discuss in a few weeks. Yeah. Okay. So elliptic curve ops. So, in fact, the snarks with the shortest proofs and fastest verifier, they do elliptic curve operations because of the use of KZG commitments. They do involve a trusted setup. That's sort of what enables their verifier to be so efficient and the proofs to be so short. Is this trusted setup unlocks that. And with any elliptic curve operations, you have the following giant headache for recursion. So any elliptic curve group, the group elements in the elliptic curve group are actually pairs of field elements satisfying some equation. And I never quite remember the elliptic curve equation. I actually think this is, I try to mention whenever I can that, like I barely know how elliptic curves work because people are always asking me, like, do I have to understand elliptic curve groups to understand snarks? And I always say, like, no, I barely understand elliptic curve groups myself. You can largely treat them as a black box. But for recursion, you do have to know a little bit about them. So yeah, so they're pairs of group elements are pairs of field elements x comma y satisfying like y squared equals ax cubed plus bx plus c or something like that. And this field where such that group elements are pairs of field elements, this is called the base field of the curve. Okay. But there's another curve associated with the group. The size of the group, so the number of pairs of field elements that are in the group that satisfy this equation. So the size of the group is basically the number of pairs of field elements that satisfy the equation, is itself a prime. Let me call it P. Okay, and FP, the field of size P is called the scalar field of the group. Okay, and that means let me just move this reminder later. Oops. Whatever. I'm just going to erase it and hope I don't forget. I probably will forget because my sleep debt has gone almost to infinity. But anyway, please remind me if I don't say anything more about bulletproofs today. So yeah, so basically, like group elements are associated with elements of the scalar field. Okay, and what's really important here is the scalar field and the base field are not the same. So this is never the same as the base field in cryptography, and the reason is so there are elliptic curve groups where the scalar field and the base field are the same, but discrete logarithms are always easy to compute in such elliptic curve groups. And the whole point of these groups is at a minimum, discrete logarithms should be intractable to compute. Otherwise, any commitment schemes that use these groups won't be binding, right? They just won't be secure. So that is the key engineering, like technical headache that comes from trying to do elliptic curve group operations inside a circuit. Because what's happening is, the verify, like to do group operations, like to take two group elements, and if it's a multiplicative group, to multiply them together, right? That involves base field operations. So like, one group multiplication, if it's a multiplicative group, is like something like 10 base field operations. Okay. But again, the base field is the group elements we think of as living in the scalar field. But basically the verifier that has to do the group operations for the group that sort of represents the scalar field has to do base field operations. So there's sort of a mismatch. So what's happening is if you have a snark, like let's just say Planck with KZG commitments applied to a circuit C. Okay. Then KZ, like that circuit will be defined over the scalar field of the group that KZG is defined over, which in Ethereum settings would certainly be BN254 because that's the Ethereum precompile that the only Ethereum precompile cryptographic group. And so you're if the prover is making a statement about a circuit that does addition multiplication over the scalar field, the verifier, like the KZG verifier or let's say the Planck verifier, has to do operations over the base field. Okay, and they're not the same field. Okay. So what that means is you start, like the prover wants to prove it knows a satisfying assignment for circuit C over the scalar field. Okay. If you wanted to compose that snark with another snark, in order to take the verifier of the first snark and have it be a small circuit, you'd want that circuit to be over the base field. Okay. So to turn V into a small circuit, C prime, you want C prime to be defined over the base field. Okay. It's a different field. Okay. And potentially you actually have problems here, especially. So did we talk about bulletproofs last time or KZG? I don't even remember. Everything's a blur. KZG commitments use pairings, right? And you think, yeah. So what this means is, in order to do this, you need, okay, to apply a snark to C prime defined over the base field, right? If you want to use that snark to use elliptic curve based polynomial commitment schemes again, you need a cryptographic group whose scalar field matches, is the same as the base field of the first group. Which, I just for concreteness said the first group was BN254. Okay, this is actually a problem today, right? Because there is an elliptic curve whose scalar field matches the base field of BN254. There's an elliptic curve group called Grumpkin. So it has this property. Grumpkin is for it's for BN254. So it has this property, but Grumpkin is not pairing friendly. And KZG needs pairings. Okay, so you can't use, in this case, like you could use Grumpkin, that'd be fine, but you can't use KZG commitments again, right? And that's just one, this specific issue. So if you go back, I don't know, like 5 years ago, I think we hadn't yet cooked up this elliptic curve group Grumpkin, who's I don't know when we cooked it up. I think maybe the Aztec folks did, and I suspect it was in the last 5 years. I don't know for sure. But the point is, someone had to cook this up, right? So in order to make recursion work out here, if your first snark worked over the curve BN254, someone had to cook up Grumpkin, an elliptic curve group in which discrete logs appear difficult to compute, whose scalar field matches the base field of BN254. So this is an issue you had to deal with, and we've dealt with it, but actually only sort of incompletely, if you will, because it's not pairing friendly, and people really like KZG commitments, and they require pairings. So that's the issue, and so at this point we've sort of solved this problem in a lot of settings, and so I'll give you some examples. BN254 and Grumpkin are like one particular example of elliptic curve groups that match up in this way. where the scalar field of one is the base field of another. But I'll give you some more examples and elaborate a little further on the situation. But let me just pause here and see if this made sense and if anyone wants to ask a question. No. Can someone confirm like my internet hasn't gone out? Because that's been known to happen before.
Yes.
Okay, cool. Cool. All right. So I'll give you some more examples. And okay, so now so far I've only talked about what's called depth one composition or recursion. And that's where you take, snark one and, the proofs are say bigger than you want or something. So rather than taking the snark one proof and declaring it the final proof, instead you use snark two to prove, a snark one proof. Okay. In that situation, you really just need these two curves where the base field of one matches the scalar field of the other, and that's all you need. Okay, but people often do deeper compositions, and I'll explain in more detail why. There are a lot of reasons that comes up. So I'll say more about that shortly. In that case, you need more than just this. I view it as a length one path where you have like the base field of one matches the scalar field of another. And if you want to do depth two composition, you'd then want the how would it go? Too sleep deprived to. I'm gonna get them mixed up, but okay. So let's see, base field, scalar field. Okay, so let's say this was the scalar field for the snark one group. This was the no, we want the base field for snark one. Sorry, to match the scalar field for snark two. If you then wanted to do another level composition, you'd want another group whose scalar field matches the base field of this node in the path. And so every time you do another level composition, you need potentially another group. So if you use snark two to prove a snark one proof, now if you want to use snark three to prove a snark two proof, you need this this third group. If you want to use snark four to prove a snark three proof, you need a fourth group and so forth. And if you want to just keep going as long as you'd like forever, what you really need is a cycle. And people's favorite cycles are length two cycles. So basically this would be two groups. People call this a cycle of curves, or sort of a length two cycle of curves, where the base field of one equals the scalar field of the other, and also vice versa. The base field of the other one equals the scalar field of the first one. And that lets you do arbitrary depth recursion. So you take your snark one and you use snark two to prove the snark one proof, but snark two would be defined over so we'll call this group one and this group two. So snark two would be defined over group two, but then you'd use snark one to prove the snark two proof, which is fine again because you have this nice matchup. Then you use snark two to prove the snark one proof, and you just go back and forth between the two groups. So the snark two verifier gets represented over one field, and the snark one verifier gets represented over the other field. So people call this a cycle of curves. It's you need this for arbitrary depth recursion. So let's briefly talk about what cycles of curves are known. So we already said, so BN254 and Grumpkin, they form a cycle. But again, remember, BN254 is pairing friendly, so you can do KZG commitments over it. But Grumpkin is not. Okay, something to keep in mind. There's what are called the pasta curves. And here, the Zcash folks have a very highly optimized implementation of this. Very nice piece of engineering. And so neither of these support pairings, FYI. But for a lot of snarks, you don't need pairings. In particular, if you want to use bulletproofs as your polynomial commitment scheme, which is I think what Zcash uses today, you don't need pairings, and pasta curves are fine. And in particular, again, in a few weeks, we'll talk about Nova. Nova does not need pairings. So you could do Nova over the pasta curves. Nova does at the very, very end use like some snark. And if you wanted that snark to use pairings, you could not use the pasta curve. You'd have to do something like BN254 and Grumpkin. Let's see, those the main cycles to be aware of, perhaps. And then, so maybe those are the main cycles to be aware of. Oh, there's one more. So a lot of digital signatures on blockchains, I think in particular Ethereum and Bitcoin, both use some curve SecP something. I always forget what the suffix is. And that's involved in a cycle with another curve called SecQ something. So you could, if you want to prove knowledge of digital signatures authorizing Ethereum or Bitcoin transactions, you could use this cycle of curves and do snark composition there, and everything works out nicely. And then the last thing I'll say is, if you want, yeah. So okay, yeah. Here's a challenge that's unresolved. We do not have nice cycles of pairing friendly curves. Where both curves in the cycle support pairings. Okay, so this is what you would want to do, like arbitrary depth composition of like KZG based snarks or growth 16 or something, and we don't have it, so you really can't do that without paying an enormous performance hit. So the best known cycles of curves we have in this case is something called MNT curves, and I just think they're, in order to get I think even 80 bits of security, which is really not enough. So even for 80 bits of security, I think that they're just huge. Like the scalar field and base field involved. The base field involved is maybe like 700. I don't know, 700 plus bits or something. We prefer to work over base fields that are at most say 381 bits. That's BLS 12381 is a popular pairing friendly group, and that's about as big as we already don't really love that the base field is 381 bits. It might be even worse than that. It might be in the thousands. If you go back the early days of recursion, people were doing this anyway. They're like, we really want to compose pairing snarks that use pairings. Why did they want to do that? It's because KZG commitments and whatever, growth 16, which also looks a lot like KZG commitments. The snarks with the lowest verifier costs use pairings, right? And you want the verifier to be able to get turned into a small circuit. So you really, ideally, if you're looking to do snark composition, the first thing the snark you want to compose, if you're just starting out anyway, doing things naively, you'd want to pick a snark with like the best verifier cost. Well, what snarks have the best verifier cost? The snarks that use pairings. Okay, but then you have a problem, right? Because in order to do deep recursion with pairing friendly curves, well, you need a cycle of pairing friendly curves, and we just don't have good cycles of pairing friendly curves. And in fact, some barriers are known. I don't know any details, but I know there's been some work identifying barriers to improving the state of affairs. So it's known that like curves that support a cycle and are pairing friendly just either have to be really big, involve big fields, or else they somehow have to look different than the kinds of curves we know today or something like that. So today you'll never see people talk about doing deep recursion of snarks that involve pairings. Again, if you can repeatedly compose one snark that uses pairings and one that doesn't, using the Grumpkin BN254 cycle, but you can't compose a snark that uses pairings with itself over and over again, unless you pay the enormous performance price of using MNT curves. Okay, let me think. Is that everything I wanted to say about this issue? Yeah, maybe that's fine for now. So yeah, this was a big I don't know, if you're trying to implement snark composition, if you've got a hashing based snark, the today you'd want to think about using a snark-friendly hash function. Although there are projects that are starting to realize that standard hashes that aren't snark thought to be snark friendly are still maybe friendly enough to do recursion anyway. And I think that's going to get amplified a bunch next week, that viewpoint. But if any of the snarks you're dealing with involve elliptic curve based commitment schemes, you have to be very much in practice be aware of this issue that scalar field and base field of any elliptic curve group are not the same. Okay, questions? All right. Okay, so I think now then.
Sorry, a quick one. Yeah. So when you, just to clarify, so when you say that when you have this cycle of curves where only one of the curves supports pairings, so you mean okay, so you have two curves. Sorry, is it one curve or two curves? So you have two, or you have two groups, is it? Or?
Yeah. So think of Grumpkin and BN254. So the scalar field of Grumpkin is the same as the base field of BN254, and vice versa. Yeah.
Oh, okay. All right. Okay. And okay, but there isn't a pair of curves which has this sort of base and scalar field relationship where both of the groups are equipped with a pairing. Okay,
that's right. That's right. Yeah, if you want them both to be equipped with the pairing, you got to go to MNT curves, and they're just like your performance is going to be garbage. Yeah.
Okay, thanks.
Yeah. Yeah. So as we'll see, like with Nova, Nova doesn't need pairings, throughout its entire like execution until the very, very end. And so Nova involves recursion. It'd be fine to use this cycle. As you do one step of the composition, working over BN254, and the next step over Grumpkin, the next step over BN254, the next step over Grumpkin. And as long as you sort of finish up like living in BN254, you can then at the very final step apply a pairing based snark. But the point is, you didn't need pairings until that very final step of Nova, where finally you might want to apply a pairing based snark to get the proof as small as you can. Yeah, and we'll see as I'm about to, after we talk about security a bit, I'll then talk about incrementally verifiable computation, or also I just think of it as snarks for iterative computation. And you'll see why you might actually want, why people started working on snark composition. Literally, the idea was you were going to like take growth 16 or its predecessors and compose it with itself over and over and over again. But you would not do that today for a number of reasons. One of them being what we just discussed. You'd have to use MNT curves, and your performance would be awful. All right. Yeah. Okay. So let's talk about security a bit. Okay. So, the way I describe snark composition, it's like feels intuitively obvious that it's secure, right? Like if you use snark 2 to prove a snark 1 proof, well, that should be secure, right? Because snark 2 is secure. So if you find a convincing proof, for this composed snark, you must actually know the snark 1 proof. And then snark 1 is secure. So the fact that you know the snark 1 proof means you actually, your original claim was true, right? But if you actually work through the security analysis, you wind up with a couple of issues. So let me flag both of the issues. I'll start with the issue of extractor runtime. Okay, so I just gave you like an intuitive explanation for why snark composition should be secure, but formally, a snark, the K in snark needs knowledge sounds. So formally, to show that the composed snark is secure, we have to identify an extraction procedure that can take a prover capable of producing convincing proofs for the composed snark and pull a witness for the original claim out of the prover's head. Okay, and so how do we do that? Okay, so remember the way the composed snark works is we applied snark 2 to the verifier circuit for snark 1, right? And so what we're going to do, we're sort of going to construct our extractor in sort of a two-step process. So first, what happened to my pen here? Sorry, 1 second. My pen has died. There we go. So first, we want to, let's see, identify a convincing prover for snark 1 applied to the original claim, which was I know a satisfying assignment for C. My pen must be out of batteries. That's really frustrating. Out of charge. Does it tell me? Okay, I'm just gonna. I think it charges pretty fast, so let me just verbally talk for a minute. Right. So first, we're going to identify a convincing prover for snark 1 applied to the original circuit C. Once we've done that, we can apply the extractor for snark 1 to pull the witness out of this snark 1 prover's head. Okay. I mean, the tricky thing here is what we're given is a prover for the composed snark, like snark 2 composed with snark 1. Okay. But to actually identify the witness, we need a convincing prover just for snark 1, because snark 1 is what's used to sort of, in the composition to prove the original statement. Okay. And so, anyway, let's first identify a convincing prover for snark 1 applied to the original statement, C. I know a satisfying assignment for C. Okay, so what is that prover? So what we're given is a prover for the composed snark. So let me call that composed prover like PC for composed. And so the composed prover produces convincing snark 2 proofs. Okay. And snark 2 is knowledge sound, so it has a knowledge extractor. Okay, so we can take the snark 2 knowledge extractor, let me call that E2 for snark 2, to this composed prover, which produces convincing snark 2 proofs. Okay, to pull a witness for the snark 2 statement out of PC's head. But a witness for that statement is just a snark 1 proof pi, right? Because snark 2 was used to prove, snark 2 was used to prove I know pi, I know a snark 1 proof pi. Okay, so our prover that produces convincing snark 1 proofs pi, okay, is obtained by applying the snark 2 extraction procedure to the composed snark prover. Okay, so our convincing snark 1 prover, let me call it P1, is obtained by applying the snark 2 extractor to the composed prover PC. Okay, that is the convincing snark 1 prover. Okay, now that we have the convincing snark 1 prover, the way we actually get the witness is by applying the snark 1 extractor to P1. So it spits out the witness for the original claim, C. Okay, great. So it was a slightly funny process where we obtain P1 by applying an extractor to PC. Okay, and then we obtain the witness by extracting from P1. Okay, great. So it's secure, right? The composed snark is secure, but we do have the following technical issue that I want to highlight. Okay, so a lot of extractors work via rewinding. Okay, anytime well, let's not get into it. If we're bulletproofs, I think last meeting, or was it KZG or bullet? When we discussed bulletproofs, we talked about how the knowledge extractor like rewinds and restarts the prover many times, right? And so if the extractor does rewinding, okay, that means it calls PC multiple times, okay. Let's say the extractor, like the bulletproof extractor, calls. So this procedure, E2 applied to PC, it like runs PC many times. I don't know. Let's say n squared times. Who knows? And let's just say n squared times. Okay, which means and let's say that the SNARK1 extractor does the same sort of thing. So let's say E1 runs P1 also n squared times. Okay. Well, if I ran P1 n squared times, but P1 itself runs PC n squared times, the runtime of this whole procedure here is runs PC n to the fourth times. Right. This is the issue I want to highlight. Okay. So let's say you did a depth 3 composition, right? This problem gets worse and worse and worse, right? So this here is a way to output like convincing SNARK1 proofs. But if there was like yet another level of composition, you then have to extract from this thing, right? And so you'd wind up calling this thing n squared times, right? Which means, the composed SNARK prover actually winds up getting called like n to the 8th times or something. And then if there was yet another level of composition, it'd be n to the 16th times that the composed prover gets called, and so forth, right? Basically, if every extractor takes the prover it's extracting from and runs it many times, then when you do this like sort of weird composition of, you get a prover by extracting from the previous prover, you get a prover by extracting from that, you get a prover by extracting from that. The number of times, you wind up actually running like the prover you started with just blows up exponentially with the depth. So it's like n to the 2 to the depth of the computation times or something like that. It's really bad. It's at least n to the depth. I'm too sleep deprived to figure out if it's that 2 to the depth should be in the exponent or not. Anyway, great. So that is a problem to be aware of. So based on how a lot of knowledge extractors work, you actually have this potential security loss according to the security proofs anyway, where the deeper you do the composition, the less concrete security you have, right? Because if the knowledge extractor takes an exponential amount of time, there's no, that becomes meaningless, right? You're saying, well, given a prover that can produce a convincing SNARK proof, I can identify an exponential time algorithm to identify the witness that the prover is claiming to know. But typically one could brute force find a witness in exponential time anyway. So that's like a trivial statement, right? So in principle, anyway, like while we think SNARK composition actually results in like zero degradation in concrete security, the way a lot of knowledge extractors work, we can't rule out like a massive loss in concrete security by doing SNARK composition. Okay, and there's actually a recent paper, so a counterpoint to worries about this, because people just compose SNARKs all the time and assume that there's literally zero loss in security. So a counterpoint is that in what we call idealized models, like say the random oracle model, we actually have straight line extractors. That is, the extractors just run the prover once. They don't have to rewind and restart the prover multiple times. And in that setting, this blow up in extractor time doesn't happen. So that's a simple observation. And so this new paper by Alessandro and others sort of does some extra work to sort of make formal like some implications of this. But basically, you could take the fact that we have straight line extractors in idealized models like the random oracle model, which a lot of our SNARKs wind up, their security proofs work in these models, as some evidence that the security degradation that comes from a blow up in extractor time just doesn't actually have to happen at all. So that's a point I wanted to raise. But I guess the way you should the high level interpretation here should probably be, in practice, it's fine to just take SNARKs and compose them and assume there's no loss of security. but we don't actually have a great theoretical understanding for like support for that being okay. We just don't have any attacks, and we do know due to this straight line extractor stuff that any attack on the composed snark would have to do something like treat a cryptographic hash function differently than a random oracle, and we generally don't know attacks that exploit that in any way. But I do know theorists who are quite concerned about this because it's known that the Fiat-Shamir transformation, which is the snark design technique that uses a random oracle, basically the reason we do work in the random oracle model in our security proofs. It's known that the Fiat-Shamir transformation is actually not secure for some contrived statements when you instantiate the random oracle with the concrete hash function. Now, these contrived statements are contrived, so we do think that for the statements people are actually applying Fiat-Shamir to, like today, they are secure. But these contrived statements are sort of self-referential in a way that is very much of the flavor of snark recursion, where you apply the snark itself to the snark's own verifier. And so I know like theoretical cryptographers who are quite concerned, like they feel like snark recursive composition to snarks is very much of the flavor of exactly the sort of statements we know Fiat-Shamir is not secure for. So they become worried that in order to do the recursive snark composition, you do have to sort of take the random oracle and replace it with a concrete hash function in order to take the verifier and turn it into a circuit. And the whole thing just gives them, the heebie-jeebies. And while they don't actually know an attack, it freaks them out. Okay, so just some issues to be aware of with security of snark composition. But in practice, people just do it and assume that there's no loss of security, and it's probably fine. But there are some people who are a little bit concerned about that. Okay, so that is snark composition. I did want to say a little bit about IVC and snarks for iterative computation. I don't think it will take me that long, but it'll actually be really important context when we discuss NOVA in a few weeks. So let me just pause here, see if anyone wants to ask any questions. And after any questions, I'll try to limit myself to 10 minutes on this. Normally when I say 10 minutes, it takes 30. But yeah, I'll try to do 10. So anyway, does anyone want to ask any questions? Okay. All right. So this extractor stuff, while it's, pedantic and technical, didn't confuse anyone so much that they wanted to ask anything about it.
Can you elaborate a little bit more on the contrived statements?
Oh, I can try. I always get myself tied in knots trying to remember what the statements are like. So, okay. Let's see. I once spent a session trying to literally like tell everyone what was a statement where when you apply Fiat-Shamir to it and instantiate the random oracle with a concrete hash function, it's not secure, and it was a disaster. I just couldn't quite. It's a little like the main idea is like clear, but then the details are tricky, and I got wrapped around the details. But let me briefly try again. So. Okay, the papers like to give protocols for what they call the empty language, meaning the verifier should always reject. So if you ever convince the verifier to accept, that's bad. That's like bad for security. Okay, and so the natural protocol for the empty language is one where the verifier never pays any attention to the proof at all and just rejects, right? But you can give contrived protocols that are still secure for the empty language. Because the prover has to get really lucky to convince the verifier to accept, but there is some small chance the verifier accepts. Okay, and so here's a contrived protocol for it. Let's say, I'm probably going to mess this up, but let's say the prover just sends a message to the verifier. The verifier picks a random hash function, hashes the message. And if the hash of the message is a description of the hash function, right? As I said, it was contrived, right? Something like that. the verifier picks a random hash function, hashes the prover's message, and looks at what comes out. And if what comes out is literally a description of the hash function it just used to do the hash, so like h of m equals h, where by h I mean like a description of the hash, like a computer program or something, something like that, implementing the hash, the verifier will accept, right? And it's incredibly unlucky the prover would have to get incredibly lucky, since the prover doesn't know in advance what hash function the verifier will use, for it to send a message and have the hash of that message be the hash itself. Okay. Let me make sure I'm doing this right. Okay, I probably messed this up, but this is of the flavor of let's see. Yeah, no, this might work out. So now so this is a secure protocol, because the prover has to get super lucky in its choice of m or something for m to hash to the description of the hash function, right? But now when you instantiate the random oracle, yeah, actually, let me redefine this. So for h of m to equal, I'm probably screwing this up again. I don't know. H of m to equal h of h. I don't know. So, the hash of the hash of the hash, hash of the description of the hash. But I don't quite remember the details. But now, if you apply fiat Shamir and instantiate the random oracle with the concrete hash function, basically the prover knows what h is, right? So it can just set m to be that hash function, and so it can always succeed in passing the verifier's check. All right. So. Okay, this is like close enough to what people are doing that I'm comfortable. I gave you like the rough idea. So very, very contrived protocol. You'd never actually cook up a protocol like this. But it's a secure protocol when the hash function is like, chosen truly at random by the verifier, but it's like totally insecure once the prover knows in advance what the hash function is, because it can just set m to be the hash function. But despite this being super contrived, it is of the flavor of what we prove when we do snark recursion, with hashing-based snarks, right? With snark recursion with hashing-based snarks, like you wind up applying the prover to the verifier as a circuit. The verifier as a circuit does a lot of hashing. So you're proving something about hashes. This is a statement like about hashes, right? I mean, maybe I shouldn't babble for too long, but it feels to people who study this stuff, snark recursion feels very similar to this sort of contrived protocol where the verifier hashes the prover's message and accepts if the result is something that itself like refers to the hash function. This very self-referential thing where you're doing hash, you're proving something about hash, the hash function itself or something like that. Was that a little bit instructive?
Yeah.
Okay. Okay. So you can have a look at papers. There's, I recommend, and I think this example I'm trying to cook up, there's a paper of Ron Rothblum and I think his student on the insecurity of Killian or something like that, Killian-based snarks. And it has an example, I think, like one of the nicest examples of this. And, he basically gives, so Killian is like the earliest, simplest way. You take like a PCP and you Merkle hash it and apply fiat Shamir, and like that gives you a snark, right? So he, it has a nice example where they cook up a very unnatural PCP. You would never actually design this PCP, but when you take this PCP, you apply Killian's, transformation to turn it into a snark. And when you actually instantiate the random oracle with a concrete hash function, it's not secure, no matter what hash function you use. And so again, it's actually showing that the way we design snarks today is not secure, unless you start making assumptions about, like the information theoretic underpinnings that we apply the cryptographic transformations to. Now, we still think that that doesn't mean we think like, people using Fry today and are deploying something insecure. Because Fry itself is not some contrived, made up PCP that was made up specifically to make the cryptographic transformation to a snark insecure, right? Fry is some natural protocol that was designed to give a secure, to give an efficient snark. And so probably when you apply Killian's transformation, like to Fry, you do get a secure snark, but it's just highlighting that if you just take an arbitrary contrived PCP and compile it into a snark the way we're used to compiling PCPs into snarks, what comes out might not actually be secure. So, yeah, I'd say just have a look at at this paper, and you'll get more details. Okay. Thanks for the question. Other questions?
So I had the.
Sorry, is it my internet that's cutting out or yours?
So you would need sorry. Oh, so you would need like a cycle of you need a cycle of curves where you have where both support pairings in the case where you want to support like an arbitrary composition of pairing based snarks. But if you don't need if you don't need arbitrary composition of them, so you just just compose maybe one pairing based snark with another pairing based snark, then you're okay with not needing something like MNT curves.
Yeah, great. Yeah, great. I meant to mention this and I forgot. So there's a curve called BLS 12377, which is specifically designed so you can do depth 1 composition of pairing based snarks. And so it's of pairing based snarks. So it's not a cycle. So you have BLS 12377 and some other sister curve. I don't know what it's called. And let's see, the base field of 12377 equals the scalar field of the other curve, or maybe I have them backwards, but whatever. But the revert, it is not the case that the base field of the other curve equals the scalar field of BLS 12377. It's not the case. So that is, you can do depth 1 composition efficiently, but you can't go anywhere past depth 1 efficiently. And so there is this came out in like the Zexi paper because they wanted to do depth 1 composition of pairing friendly snarks in that paper, so they cooked up this curve. There is like an Ethereum and EIP proposing to make this curve a precompile. I don't think there's much momentum behind that, but there is an EIP. So the real issue is the cycle of pairing friendly curves when you want to do arbitrary depth composition. Depth 1 is okay. Does that make sense?
Yeah, that's helpful. Thanks. Yeah. So so then for the cycle of BN whatever it is 25 something and
Grumpkin, yeah.
And Grumpkin, yeah. So for that one, you can do an arbitrary composition then, but is it where the snarks sort of alternate, between pairing and non-pairing based? Is it?
Yeah, exactly. Mm-hmm. And but where I expect that to really be used is probably something like Nova, where you don't need pairings at all until the very end, where if you want your proof to be as small as possible, then you do finally want a pairing. So in that case, but yeah, in principle, like you could take a pairing based snark and a non-pairing based snark, and you can compose them arbitrarily deeply by going back and forth between Grumpkin and BN254. And it's just, anytime you want to use the pairing one, you better be over BN254. And anytime you're over Grumpkin, you have to use the non-pairing one.
And why is it useful, you think, in particular for Nova?
Oh, just because so Nova proofs, if you don't the way to get the shortest proofs with the fastest verifier is to use KZG commitments. So those are the proofs people want to get on chain. So if you didn't use pairings, the way to get the proofs as short as possible would be like bullet proofs, which have logarithmic size proofs instead of constant, instead of 3 group elements or whatever KZG based things would be 3 to 10 or something. I guess Marlin would be like 10. Bullet proofs would be like 2 log n or something like that. So talking about 2 log n, think of it, I don't know, 40, right? And moreover, the bullet proofs verifier is like linear time instead of just doing a couple pairing operations. So you're just going to wind up with the high level, you're just going to wind up with higher verifier costs if you don't use a pairing-based snark at the very end of Nova. Does that make sense?
Yeah. Okay. So I see. Yeah. So, but do you need the arbitrary composition depth of the cycle to do that last step of Nova? Or?
Okay, so Nova does deep composition until the very, and then at the very end, it does one more composition, right? And so it's in that one final composition at the very tip that you might want to use a pairing-based snark to get the final proof as small as possible. So Nova is all about deep composition, but nowhere does it need pairings until the very end, where if you want the proof as small as possible and verify as fast as possible, that's when you would want to use pairings.
Okay.
And this might make more sense when we cover Nova in a couple weeks.
Sure. Thank you.
Yeah, thanks for the question. I hope that was at least a little bit helpful, the responses. Okay. All right. Yes. I guess that's everything I wanted to say there. So yeah, let's talk about snarks for iterative computation. Again, I don't think this is going to take long. Thanks for the questions, even if my answers were so iterative computation, that's when you have a relatively simple function f, and the prover wants to prove it just applied f many, many times. Let's say to some, public input x, the verifier knows x. Now this might seem like a very simple contrived setting, but actually it's almost, in a sense, it's fully general, because if people talk about ZKVMs, this is fully general computation. Like the prover wants to prove it correctly ran a computer program on some witness, where the computer program is specified in the assembly language of what snark people call a virtual machine. Others might call an instruction set architecture. Others might just call a CPU architecture. It tells you basically everything that the machine does. It's like a very simple version of your laptop or something like that. So like you can compile any computer program down to the RISC-V CPU, the RISC-V virtual machine, and then use ZKVM for RISC-V. That's what the RISC-0 project is targeting. That's what my work called Jolt targets. And so that's as general as can be. Prove you ran an arbitrary computer program. And what VMs do is they basically just iterate the same simple function f over and over again. That function f being what's called like the fetch, decode, execute cycle of the virtual machine, where the virtual machine just fetch means like read what's called the program counter. That just tells the computer program like which primitive instruction to execute next. Decode just means like kind of understand, make the computer program understand the instruction you just read from the program counter. And then execute just means like actually execute that instruction, and update the program counter as needed. And so this fetch, decode, execute, that's like a very simple function f in the scheme of things. The only component missing that the ZKVM needs that iterative computation does not have is memory, like access to like 3 gigabytes of memory or something, so that the computer program can store data that previous instructions had output or something like that. But basically, once you have a snark for iterative computation, you're sort of halfway to a ZKVM. If you combine a snark for iterative computation with what's called memory checking, and by the way, you can just use Merkle trees, and that's what most of the projects do today. Though I think they're quite expensive. But anyway, you can just use Merkle trees to maintain memory, combine it with a snark for iterative computation, you have your ZKVM, and it's fully general. Okay, iterative computation comes up outside of ZKVMs too. One big example in blockchain space is for what's called verifiable delay functions. So like Ethereum's been talking for a long time about using these to try to make it more difficult or impossible to predict like who the next leader will be. The leader being like the person who decides like, which transactions get into the next block or something like that. So a VDF is a function. Delay function means you inherently need a certain amount of sequential time You need at least a second, no matter like how many GPUs you have, you still need at least a second or something to compute the delay function. But verifiable means like once you've computed the delay function, it's like super duper duper fast to compute a proof that you correctly computed it. Okay, so they're thinking about putting a VDF into the leader election, basically so that everyone is going to have to spend at least a second or something evaluating the VDF in order to figure out who the next leader is. But once that leader or someone on the network has spent that second and the necessary work to evaluate the that function, they can quickly prove to everyone else in the network what is the output of the function. So in that way, like kind of verifying who the next leader is easy and fast. But figuring out who the next leader is takes at least a second, even if you have like a giant cluster of GPUs or something. And the leading proposals to design VDFs basically take a relatively simple function, f, and just iterate it sequentially, right? And the rough conjecture is the fastest way to compute f of x, like parallelism doesn't help because, how are you going to start computing f of x until you know f of x? How are you going to start computing f of that until you know that, and so forth? The Ethereum cryptography group just put out a note where they actually found slightly better algorithms to parallelize some of these things. And so they're sort of putting on ice the plans, but those algorithms they found are only slightly better than complete brute force and so forth. So anyway, this is still an important other example where iterative computation comes up. So it's both kind of fully general, but also there are very, very specific important applications that are, exactly iterative computation. Okay, now let's, one way to give a snark for iterative computation is to just have one giant circuit that applies F over and over again, and just apply any snark that you want to that giant circuit. Okay, this has two problems that I would say performance-wise. The one I care about the most is space complexity. So the prover has to write down that whole circuit. With most snarks, it would store that circuit in memory. It would actually evaluate every gate in the circuit. And then, if you're using Fry, you're then going to apply an FFT to, like every gate in the circuit. And that's going to like double or quadruple your space usage even, on top of that. And so you wind up, even for pretty simple statements, I kind of argue with people over just how simple they should consider it. I consider it very simple. Like Polygon ZK EVM is, over 250 gigabytes of space for the prover, and it captures, like 10 million gas of Ethereum transactions. I consider that that's very simple. It's only 10 million gas, like every blockchain node in the network is doing that over and over, all the time. That's not a complicated statement. So the point being that if you're applying this F many, many, many times, turning it into one giant circuit, the proof is going to run out of space and fall over and not be able to compute a proof. You're going to have a problem. So that's one reason you wouldn't want to just turn F of X into one giant circuit. But another reason, and this is what IVC refers to, is you might have the following goal. You might want to run a computation, for a long time. And at all steps of the computation, just the prover you want to have in its head a running proof that everything it's done up to now has been correct, right? So it applies F once and it computes a proof that that application of F was done correctly. Then it applies F a second time and you want it to be able to quickly update the proof to capture that both applications of F were done correctly. Then you apply F again and you want it to be very fast to update the proof to capture that, all three applications of F thus far have been correct. And a benefit of that, in addition to, kind of the prover not really storing anything extra beyond, the running proof, which is great for the space complexity of the prover, is things like, imagine a roll-up that, doesn't have super high volume or just wants really big batches or something like that. It wants to roll up a lot of transactions before posting a proof on chain to get really good amortization of gas costs. Well, with the what I call the monolithic snark approach of just turning, the whole computation into one giant circuit, you sort of just have to wait around until all of the entire batch has been materialized, until enough transactions come in to fill your batch. Okay, but with IVC, as soon as like even one transaction comes in, you can like here F is sort of just the function that processes blockchain transactions. So you can start processing that transaction and immediately start working on a proof, that you process that transaction correctly. And then, when the next transaction comes in, you start, another application of F. And so you basically don't have to wait around for your batches to fill up. As soon as transaction comes in, you just, fire up the prover and just keep updating the proof as more and more transactions get processed. Okay, so those are motivations for doing something more sophisticated than just turning all these applications of F into one giant circuit and applying your favorite snark, whether it's Planck or Growth 16 or Starks or whatever to that circuit. So let's talk about how you would achieve this goal of having a running proof that's sort of capturing that all applications of F so far are correct. So with one application of F, so say the prover claims that f of x equals y1. Okay, so it applies F once. So there's sort of nothing you can do other than just apply your favorite snark to a circuit implementing F. So let's say the prover does that. So it obtains a snark proof pi that this claim is true. Okay, so we've successfully proved the correct application of F, one application. Okay, now say the prover applies F again. So it claims that f of y1 equals y2. Okay, now to get a proof that captures both of these applications of F being correct, you actually have to prove two things. You have to prove A, that f of y1 equals y2. B, you have to prove that y1 equals f of x. You put these two things together and you get that y2 is in fact f of x. And that's what we want the proof to attest to. Okay, so what the prover would do, and this was the way people originally designed IVC schemes, and this is exactly why they wanted to basically take Growth 16 and compose it with itself over and over again, and you run into the issues with cycles of pairing friendly curves. They would obtain what's called an augmented circuit. Okay, so an unaugmented circuit would just be the circuit for F, right? So pi is like, I know, a satisfying assignment. For the circuit C, that computes F. That computes F, and applies it, on X. Okay. So this C is like the unaugmented circuit. It just computes F, on whatever input you want, you care about. The augmented circuit will have a second part. So the first part is just C, which applies F to Y1. Okay. The second part, okay, verifies pi. I know the proof pi, proving that f of x equals y1. Okay, that's the augmented circuit. So the augmented circuit applies F once and also verifies the previous proof. Okay, so and so the updated proof to capture that F was applied correctly twice is just you apply your favorite snark to this augmented circuit. So let me say, pi prime, the updated proof capturing the first two applications of F is just is obtained by applying your favorite snark, let's just say it's Planck, to the augmented circuit. Okay, great. And so now we have the running proof after step 2. Okay, now let's say the prover wants to prove that f of y2 equals y3. Okay, again, the way you're going to get the proof for that, let me call it pi prime prime, you again apply Planck to the augmented circuit. That augmented circuit does two things. One is, it applies, the circuit C computing F to Y2. And the other is it checks, the proof, I think I called it pi prime. That was a proof that Y2 is F of X. And so you just keep doing this. I'm just going to do it one more time. So, to prove that, f of y3 equals y4, you produce a proof pi prime prime, which applies your favorite snark to the augmented circuit. That augmented circuit has two pieces. You apply C to y3, and you check the proof pi prime prime that y3 is, 3 copies of F applied to X. So that's it. So the prover at all time is maintaining a running proof that all applications of its process so far are kosher. And what that means is at every step of the computation, it both proves it correctly applied F at that step, and also proves it verified a proof that what it just applied F to was the right thing. Okay. And so this is how people designed IVC initially. And again, because they wanted, they were taking the snark verifier and turning it into a circuit here, it was natural for them to try to use the snarks with the simplest verifier. Again, those involve a trusted setup and pairings. Unfortunately, you run into this cycles of pairing friendly curves problem. Okay, so that was basically the state of things until Halo came around. And Halo said, hey, we sort of don't like two things about the above. Two things, so one is its performance is bad because of cycles of pairing friendly curves, so bad. And the other is, maybe they also didn't want the trusted setup. So I don't actually remember which one they cared about more, or I know they flagged the trusted setup. I don't know for sure they flagged the cycles of pairing friendly curves, but certainly if they didn't, then it would have motivated their work even more to do so. And the problem with avoiding the pairing-based snarks here is, especially if you look at what at the time people considered like the best, like transparent snark for the verifier, it would be bulletproofs, And so remember, the Halo came out of the Zcash group, and they are using bulletproofs today. My pen's dead, but actually I probably don't need to write anything anymore. So the bulletproofs, while the proofs are short, the verifier actually is very slow. And so it actually, people call the bulletproof verifier linear time. It's actually worse than linear time. The bulletproof verifier does a linear number of group exponentiations, but each exponentiation should be thought of as super constant time. It's like 400 group operations, where 400 is really like roughly the security parameter, which we need to think of as asymptotically super logarithmic. So it's worse than linear time. And what that means is if you take the bulletproof verifier and turn it into a circuit, that circuit is much bigger than the original circuit you started with. And then if you take that verifier and turn it into a circuit, you applied bulletproofs again, and you turn that into a circuit, the circuit keeps getting bigger and bigger and bigger and bigger. So you really just can't do this, with something like bulletproofs, this composition approach. This augmented circuit will just get bigger and bigger and bigger every application of F. It doesn't work at all. So just to summarize verbally, sort of what Halo does is they observe the following. So in a snark, in really any snark, but especially when it uses bulletproofs, everything actually is really efficient for the verifier, except for checking an evaluation proof from the polynomial commitment scheme. So the snark verifier, at the very end of its checks, it has to like evaluate the committed polynomial at a certain point and check a proof that the returned evaluation is indeed consistent with the commitment. And so everything is fine for the verifier. Everything is like kind of logarithmic cost if you're using bulletproofs and most snarks, except for checking the evaluation proof. So basically what they did in Halo was they left producing and checking the evaluation proofs out of the recursion. So they did not put that part of the snark verification into the circuit that implemented the check on the proof. And instead, the way they dealt with those evaluation proof checks is through something they call accumulation. It really just means like, if at each step of the computation, the prover commits to some polynomial, there are ways, especially with homomorphic commitment schemes like bulletproofs, to sort of combine all of the committed polynomials into a single committed polynomial and wind up just dealing with one evaluation proof for that single combined polynomial. So rather than kind of recursing on the expensive thing, where there's one expensive thing at each step of the recursion, they sort of just accumulate all of the expensive things into they never do the expensive thing. They accumulate all of the committed polynomials into one and only do the expensive thing once, no matter how deep the recursion is. They do it at the very end. They do an evaluation proof for the accumulated commitment. And Nova is sort of the logical extreme of that approach, where Nova actually cuts out everything from the snark other than like the polynomial commitment. So Nova is built entirely out of like commitment schemes. It doesn't actually use like an actual snark really anywhere until the very, very end, where, you know, that's what we were discussing before about that's when you might want to use a pairing based snark. So Nova basically all it does is if you have many different, if you want to apply f of f of f of f of f of x, it sort of accumulates all copies of f into one, you know, so it like randomly combines all copies of f into one copy of f. So checking one copy of f is equivalent to confirming that all copies of f were done correctly. And then for that final sort of accumulated copy of f, you might want to apply a snark to that so that your final proof is short, you know, sublinear in the size of, you know, just even the one copy of f. So when we come back from Thanksgiving, we won't go right to Nova because I'm going to want to talk about these hashing based commitment schemes. But after that, we'll then cover Nova in more detail. And so, you know, I'm sure what I was saying about Nova today, if you haven't seen it already, didn't really make much sense. But yeah, we will see the details, and at that point, maybe you'll remember a little bit about what I said today, and it'll make more sense. Okay, so that's IBC. That's how it used to be designed, and sort of a sketch of how people would do it today. And yeah, and that's snark recursion, and those are the key issues that come up in terms of engineering it with these, you know, cycles occurs and things. And I flagged some security issues, but practitioners just really don't worry about them, and I think that's generally okay. I wanted to discuss it a little bit. So yeah, that's it. So let me know if you have any questions. Otherwise, enjoy the holiday next week if you celebrate it, and see you in 2 weeks. Questions?
Question. I always thought Halo 2 recursion referred to just doing recursion over like a cycle of curves.
Mm-hmm.
Is what you're saying like just different than that? Like there's some
Okay, let's talk about Halo 2 is sort of its own thing. So Halo was a work. Yeah, Halo introduced, it was a work. Yes, I'll take a minute and explain everything. So Halo was a work that basically explained how you could basically do recursion on snarks that use something like bulletproofs, despite the fact that the verifier of bulletproofs is linear time, which, you know, totally obviates the standard way of taking the verifier and turning it into a circuit and you know, proving, you know, a satisfying assignment for that circuit, because the circuit keeps getting bigger every time you sort of do that. And you know, and then Halo also got around this whole, you know, cycles of pairing friendly curves needed if you instead were trying to use KZG instead of bulletproofs or whatever. Okay, Halo 2, I believe the reason it's called Halo 2 is because the initial goal was to redo Halo, but rather than using, I don't remember exactly what snark they wanted to use. Maybe it was, you know, Planck applied to arithmetic circuits with bulletproofs. I don't quite remember what snark they wanted to use. Halo 2 is basically Planck with bulletproofs, but when I say Planck, I mean Planck applied to Planckish, which is a generalization of arithmetic circuit set, right? Custom constraints and blah, blah, blah. Okay, and so it's a code base that basically implements Planck for Planckish constraint systems, right? Whereas the original Planck paper only discussed arithmetic circuits, you know, the engineers, you know, realize Planck applies more generally to Planckish constraint systems. And yeah, as far as I know, Halo 2 has never actually implemented recursion. So it's very confusing now. Halo was all about recursion. Halo 2 is really just an implementation of Planck with no recursion, but called Halo 2. Does that clear things up?
Yeah.
Oh.
What's like the reason behind naming of Plunky or Plunky 2? Is it the same thing?
Okay, so Plunky 2 is basically Planck with the polynomial commitment scheme set to Fry instead of KZG or bulletproofs. Let me just think for a second. There are other differences. Starkey is non-recursive, and for air, okay. So yeah, I mean, high level, Plunky 2 is just it's Planck with Fry as the polynomial commitment, and then with recursion implemented, high level. Yeah, and Halo 2 is Planck with bulletproofs or KZG as the polynomial commitments without recursion implemented. Going a little bit deeper into the weeds, it's possible that I know that Halo 2 supports Planck-ish. That's like the kinds of constraint system they support. Plancki 2, I don't know if it's air or Planckish. I mean, they're closely related. Like Planckish is sort of like air with extra pre-processing allowed. So I don't even consider there to be a big difference between them, but there might be, anyway, there might be some slight differences in terms of the kinds of constraint systems they support. But hopefully my high level statement clarified the differences in the implementations at least a little bit. Was that helpful?
Yeah, thank you.
But I don't know for sure what the situation right now is with Halo 2 and recursion. My general understanding is it hasn't been implemented, and I don't think it's really on the agenda. But that could have changed, and I could have missed it. I could be wrong about that, so I don't want to say with certainty. It's just my general impression. Yeah. Other questions?
Do you have a recommended list for memory checking? Because I think it's a not necessarily a problem, but I'm interested. And yeah, I know about the Merkle hashing and the scheme you propose in Jolt, I think.
Mm-hmm. Yeah, I mean, I think that's basically all you really need to know. I'm trying to think if there are others. If you go into the Jolt paper, I like brain dumped different ways of doing memory checking. As I don't know how it's like an appendix. I don't know how understandable that brain dump is. But yeah, I mean, to first approximation, I think all you really need to know is Merkle hashing, which is online memory checking, meaning if there's ever a read that does not operate correctly, that does not return the right value that's currently sort of that, spot in memory, like immediately the verifier will, like detect it. There's immediately some violation of a check somewhere. And then there's offline memory checking, which means if the prover, messes up a memory read, there is not an immediate verifier check. It's everything is sort of checked all at once at the very end. And so those are, there are two extremes. There's like immediate detection and detection only at the end. And I think you basically cover your bases if you know those two extremes. If you do just want to look at something else, there's a paper called SPICE, Section 5. Section 5 is a way to sort of combine offline memory checking with recursion. What's going on is this might not make much sense, but in offline memory checking, so first you have the prover like commit to all of the reads. Like so the prover is claiming to maintain memory correctly over the course of a computation. First, you need the prover to commit to the results of all those memory reads that it was claiming to have return the right values for. Only after it's committed does it have the verifier pick some randomness to do a randomized check of the reads. Okay, the key point is if the prover knew in advance what the randomness would be in the randomized check, it would be very easy for it to find some reads that would pass the check, even though the reads are not valid. Okay, so it's really essential that the prover commit to the memory stuff, results of all the memory reads, and only then learn the randomness used in the randomized check. When you're using recursion, this doesn't work because recursion is all about sort of making the prover do the verifier's work. Okay, and the verifier's work involves that randomness used in the randomized check, which basically means you have to tell the prover what randomness is going to be used in the randomized check as soon before you go on to the next step of the computation or whatever. And so it messes everything up. And so what SPICE Section 5 does is it gives sort of a computationally secure version of that randomized check, of the offline memory checking check. So that basically, even if the prover, does know, quote, the randomness that's going into the randomized check, it still can't cheat. In a little more detail, it's the randomized check involves permutation checking. So making sure, two vectors are just reorderings of each other. And what Spice Section 5 does is it gives like sort of a permutation invariant collision resistant hash. So that is vectors that are permutations of each other will always hash to the same thing. But it's computationally infeasible to find two vectors that are not permutations of each other that hash to the same thing. Okay, and that sort of lets you do offline memory checking, even in a recursive setting, which is actually how I think people maybe should be doing memory checking in a recursive setting. It's more expensive than I would like, still much more. But Merkle hashing people do it today. I think it's okay in applications that you just don't do many memory accesses, because with Merkle hashing, you only pay the expense of checking these Merkle authentication paths when there are reads and writes. So just don't do many reads and writes. It doesn't matter that checking those authentication paths is expensive. Okay, but if you're doing a lot of reads and writes, it's awful. Like if you have a gigabyte size memory, every authentication path has length like 30. It's like 30 hashes. So turning one memory read, which your laptop does like instantly, into proving in a circuit 30 hash evaluations is not good. It's like really, really not good. And so for computations doing many reads and writes to memory, I think this Spice hash thing is better than Merkle hashing and still allows recursion. But this is basically everything that's, I sort of just babbled everything I'm aware of for memory checking to you. Basically offline memory checking, online memory checking, which is like essentially just Merkle hashing, and then some interesting handful of things here and there that would enable you to combine offline memory checking with recursion a little less awfully potentially.
How does the performance of these compare to each other?
Yeah, so I think Merkle hashing, you're going to do, like I said, if it's a big memory, like 30 hashes, every read or whatever. And, I think turning a hash function into constraints or whatever, even a snark friendly one, I think it's pretty hefty, hundreds or something. I don't know off the top of my head. So, you're talking at least thousands of constraints for every read. I think the Spice hash, I think Srinath was telling me it should only be a few hundred constraints. So I think it's significantly better. But at least for a big memory, I think it's significantly better. But again, the Merkle hash, you only pay when you do access memory. The Spice hash, the offline stuff, I mean, I guess it's also the case that I think you probably would just want to use the Spice hash if you're doing recursion instead of Merkle hashing, unless your memory is really tiny. If you're, and that actually does matter, because the way, like in Jolt, RISC-V has 32 registers. So it's got, big memory, think of it as like, you have a machine with a gigabyte of memory, but only 32 registers. The registers are the things that are like, the memory that's accessed like all the time. Every step of the computation accesses, two registers or something. And the way we deal with the registers is we just treat it as a memory, right? And it's actually shocking to me. We don't really have better ways of dealing with a memory of size 32 than how we're dealing with the offline memory checking we're doing in Jolt for the big memory. So we pay like almost the same price to deal with the registers. There are only 32 of them, as we pay to deal with the giant memory that might be size a gigabyte or something. I'm hand waving a little bit, but so anyway, I think this memory checking topic is like super important. I think it's like a key bottleneck that people kind of don't necessarily appreciate how bad a bottleneck it is. Possibly just because they're dealing with a lot of computations today that just don't do that many reads and writes. And so I think it's a key. If you're interested in learning more, I think you should. I think it's important.
Yeah, and correct me if I'm wrong. Like I feel like it's like the memory, at least right now, is like very simple. There's no, and the computation is like sequential, right? There's no I guess, concurrent access or like more fancier stuff.
You're saying like in like Jolt or something?
I mean, in just general, like
General?
in most projects.
Well, okay, so let's see. Let me think about this.
Register base, mm, yeah.
So you know, like in offline memory checking, it's let me think. It's decently parallelizable in the sense that you know, like if your computer program does like I don't know parallel accesses to memory or something, like all the prover does in offline memory checking for every read, you know, it winds up you know committing to the vector of like the result of all the reads, and then every read is like associated with an access count. Okay, so basically, every memory cell stores a counter, and every time it's read, you increment the counter by 1 or something like that. Okay, and so you really just need the prover to find a way to commit to the values returned by all the reads and the associated access counts. And so you know reads to like different memory cells do not conflict with each other in any way at all. And the only like sequential bottleneck issue here is if you have like you know different you know reads to the same memory cell or something, you know you need to make sure like they wind up with you know different access counts, you know, so that you don't have two reads with the access count 2 when one should have access count 2 and the other should have access count 3 or something. And I don't know like a more parallel version of memory you could hope for than that, because like even regular memory, you know, if you try to write to the same memory cell, you know, at the same time, you have like undefined behavior, right? Like parallel machines still have to make sure that you know you don't have two different threads trying to write to memory at the same time, or you know everything gets screwed up. So in a sense, I feel like unless I'm missing something, the way we're already doing memory checking in Jolt is kind of like maximally parallelizable already. Even if we don't have like discussion of this, but you just sort of look at what's going on and see it. But is that a little helpful?
Yes. I probably need to look more into this. Yeah.
Okay.
Thanks for the answers.
Yeah. Thanks for the questions. Okay. I have to run. So let me wrap things up here. If you do have any more questions, feel free to put them in the chat. With the break, the vacation coming up, I'll try to follow the chat more. I've been bad about that recently. In the meantime, you know, enjoy your break again, and I'll see everyone in 2 weeks. Thanks for staying so long today. Talk to you soon.
Yeah. Thank you. Bye.
Bye.
Cheers. Bye.
Bye.
Thanks. Bye bye.
Everyone. Bye.